I'm Guy Blanc from Intel, and today I would like to talk to you about some of the challenges we've had when introducing the AVX512 extension, specifically regarding mask registers. So let's get started with a small example for motivation. Looking at the following C code and the equivalent AVX2 and AVX512 code, we can see that the single XOR is matching to a bunch of instructions in AVX512. So if you notice, these instructions are prefixed with K. These are new instructions using mask registers. So this is great, right? We're using new instructions. This must be good. And well, you must imagine that all of these instructions are lightning fast and that they're faster than this XOR in AVX2. So no. And in this example, and in a lot of others, example in Scalar code, we actually saw worse performance in AVX512. Now, although AVX512 is a vector extension, you still wouldn't expect to see such a degradation in performance, right? And why are we even seeing masked code? These are masked registers, so why are we seeing them in Scalar code? This is a bit weird. Before answering this question, we're going to do a short introduction. Then we're going to talk about the Scalar code issues. And finally, I want to talk about how to represent mask registers in memory. So the AVX512 extension extends previous extensions, the AVX and AVX2. It introduces 32 registers, 64-byte wide. We call them ZMM 0 to 31. And the old XMM and YMM registers are aliased to the lower parts of these ZMMs. Additionally, as we saw in the previous slide, the K0 to 7 registers are mask registers. They're also new in this extension. And the mask registers they are defined architecturally up to 64 bits, where each bit of the mask register controls a vector element. So if the ZMM is 64-byte wide, for a 64-bit wide mask register, each can control a byte from the ZMM. Now, what do the mask register provide us? They provide us the ability to do conditional execution and to efficiently merge data into the destination. To see what I mean, let's see some masked operations. So, in masked operations, and the operation itself is not performed if the corresponding mask bit is not set. So if we have a vector division, and for the masked off elements, there's a division by 0, this division will not happen, so we will not get exceptions for this code. And additionally, the destination will not be updated if the corresponding mask bit is not set. It will be either preserved or zeroed. For some examples, this is an instruction that does addition, byte-wise, as you can see by the B. It adds ZMM1 and ZMM2, puts the result in ZMM0 under the mask register K1. Now, this is a packed byte operation. So for a ZMM register, which is 64-byte wide, we will use 64 bits from the mask register. And the masked off elements here are preserved. Another example is a quad word operation. So in a ZMM, we have 8 quad words, so we're only using the lower 8 bits of the mask register in this case. And as you can see by the Z at the end, the masked off elements are zeroed, as opposed to preserved in a previous example. Another interesting thing is scalar masked operations. This is an addition, single precision floating point addition. What it does, it treats the lower part of the XMMs as a single precision floating point and adds them under the K1 mask register. Now here, since this is a scalar operation, we're only using 1 bit from the mask register. And a bit about the mask registers themselves. How can we get them in assembly code? So the first way will be, we can have a vector compare. This compares ZMMs byte-wise and writes the 64-bit result into the K register. We can also have a scalar floating point compare, which is similar to the addition, the scalar addition we saw in the previous slide. It will compare the lower part of the XMMs as a single precision floating point and write the 1-bit result into K0. Additionally, we can copy them from a general purpose register, as you can see on the K-move on the left, and you can load it from memory, as you can see on the right. These load a word, but we can load a byte or a double word, and so on. And finally, we have mask-to-mask operations that get mask registers operands and write into a K register as destination. These are AND and OR. There are several others, but it is quite limited when compared to GPR instructions. Now, how are masks represented in LLVM IR? Well, they're not. There isn't really anything special for them, but they do quite naturally map to I1 vectors in IR. How so? We do have vector compares, so the result of the vector compares are I1 vectors, and also a condition operand for vector selects. So looking at this LLVM IR snippet, you can see the first instruction is a vector compare, and the result is later used in the vector select, and you can see it's an I1 vector. Now, this sounds a lot like we talked about in mask registers. It's quite similar, and not surprisingly, the AVX512 code equivalent to this LLVM IR is a compare, vector compare, writing into a mask register, and a masked addition. So the add and the select from the LLVM IR are combined into one assembly instruction. Another thing worth mentioning is we've introduced C intrinsics with the AVX512 extension, and some of them are, of course, masked intrinsics. And the mask types there are actually just scalar integer types in C. And we later on bitcast them to I1 vectors in the IR or even later. Now, how do we treat these in the x86 backend? So before AVX512, the I1 vectors were illegal in the backend, which means they need to be promoted to another type, specifically to fit into XMM registers. And another thing is the I1 scalar type, which was also illegal. It was promoted to an I8 and mapped to a general purpose register. Now, with the introduction of AVX512, as we saw, since it maps so naturally to I1 vectors, we've made the I1 vectors legal, and they are mapped to mask registers. In addition, we've made the I1 scalar type legal. And why is that? Well, we saw scalar masked instructions before. We saw the scalar addition, the scalar masked compare, and they all use just 1 bit of the mask register, so it did seem reasonable to make the I1 legal. And additionally, when you make the I1 vectors legal, there are a bunch of DAG nodes that come along with it that you need to support: building a vector, extracting an element from a vector, inserting one, and all of these support I1 data types, so it did seem fairly reasonable to make the I1 legal. How did this go wrong? So going back to the first slide, you can see the example. And we can notice that the Boolean b, which is here as an argument and used in the if condition later, in AVX512 it's just a XOR and it's in a GPR. But in AVX512, from some reason, it is moved into a mask register, then a bunch of computations, and moved back. So for some reason, the Boolean ended up in a mask register instead of staying in the GPR as in AVX2. Now, to better understand why this is happening, we're looking at the LLVM IR equivalent to the C code. And here you can see the B, the Boolean, is an I1 data type. So we must have done something wrong with the I1. Now, in AVX2, I1 was illegal in the backend, which means it is promoted to an I1 and assigned a GPR. It's in DIL. This is the GPR in which it came according to the calling convention. But what happens in AVX512? So here I1 is legal. It is assigned to a mask register. Sorry. And the instruction selection would try to put it in the mask register. And it goes into the trouble of moving it from the GPR in which it came through the calling convention. moving it into a mask register and doing all the computations there. That is, of course, unfortunate. And what we see here is the I1 data type now under AVX512 has different use cases. It can be in scalar integer like in this example, but it can also be a mask type as we saw with the scalar addition and scalar compare. And each of these use cases, we would like the I1 to go to a different register class. We don't want the same one. And it's the job of the instruction selection phase to make the correct decision, which it fails to do in this example. Now, this is just a bug in the instruction selection, right? We go ahead and fix it. So in this example, this is probably true. We can go ahead and find the pattern that caused this, and with some amount of effort fix this and other similar issues. It is true. But looking at another example, this is an LLVM IR snippet from a Bugzilla. And you can see the I1 here, the R, is the return value from the function bar. It is later used in another basic block, the else, in the phi. And see, the AVX512 code is again worse, and you can see the same pattern. You can see a K move from a GPR to a mask, some computation, and a move back. So this is quite similar to the previous example. Why is it different? Why is it more difficult to solve this? Because this computation crosses basic blocks. And currently, the instruction selection only works on a basic block scope. So when it needs to decide where to put the R in which register, it doesn't have all the information it needs to make the right decision. And what does it do? It places it in the default, which is currently a mask register. And, well, that's bad, of course. Now, there is an effort of developing global ISO right now. And in global ISO, we can see the entire function. So we would expect this to be solved in global ISO because we will have all the information we need to make the right decision. But we also want to solve it on the short term to make at least to emit better code. So talking a little bit about the things we thought about doing to solve this. The first thing we wanted to do is to write a path to run sometime after instruction selection and correct all the wrong decision it made. Now, the idea of such a path would be to go over the function and try to find all the computation which are done in mask registers, find what is the equivalent GPR space computation, try to compare them and see what is better. If the GPR computation would be better, just transform the function, remove all the mask code, and put it in a GPR. For the example we saw, what we would expect such a path to do is to take the computation here, replace it with the GPR-based one, and then we would no longer need the K moves, which are only moving between GPR and masks. Now, there are a few issues with such an approach. The first one is it isn't really the same code, even after the transformation. You can see a bit of reordering. There are more basic blocks here. So we might be missing out on some optimizations along the way because we've made it sometime after instruction selection. The other thing to note here is these two instructions are just generating the immediate of 1 into a register. And in mask instructions, mask-based instructions, there's no instruction to do it. There's no 1 instruction. So the XOR and the shift are just generating the value of 1. In this case, it is probably easy to recognize in a pass. But since the mask-based instructions are so, there aren't many of them compared to GPR, there could be long sequences using mask registers when the optimal GPR sequence can be just 1 instruction or at least less instructions. And it might be difficult to find all these patterns when after the instruction selection. We wouldn't want to rewrite all the patterns in the instruction selection in a pass. Another issue that we've encountered with this is an LLVM IR from the test base. It isn't really important what it does, but it expects to generate the SBB instruction, subtract and borrow. In AVX2 it succeeds, and in AVX512 it doesn't. But if you look at the code here, you can see that this is strictly GPR code. There are no mask registers here, so the pass that we've looked at, that we've suggested, wouldn't solve anything here. And why is this happening? So apparently the fact that I1 is legal in AVX512 affects several optimizations. And in this case, this is a DAC combine optimization, which did not happen, just because I1 was legal. So we'll also have to go over some optimizations and adapt them to the fact that I1 is legal. And all of these problems, including the previous slide, got us thinking that maybe there's a simpler solution to this, and that we shouldn't maybe be generating mask registers for integer code in the first place. So our second option was to go back to the core issue, which was that the instruction selection does not look beyond the current basic block, and it doesn't have all the information. So it makes a default decision, and maybe we can change the default. So the option is to make I1 illegal, just like in AVX2. And then we would expect to have a similar flow, a similar code, at least not worse code. And there will still be a problem here because we haven't solved the core issue, right? We can still have an I1 which will be in a GPR after we change, but really should have been in a mask register. So we may still need some kind of fix-up, similar to the fix-up I've suggested before. But we do claim that it will be easier to do so, because moving from GPR space to mask space should be easier, because the instruction set is richer. So for each GPR instruction, we can find one or more mask register instructions, which are the optimal one. So we wouldn't have to do the pattern matching on the source, like when moving from mask to GPR. So this is the solution that we suggest. We should have a patch for it uploaded in the future. And the second thing I want to talk about is I1 vectors and how we represent them in memory. Now, why is this important for AVX512? So we did introduce new instructions to load and store mask registers. And as you can see, it's quite easy to do so. Loading and storing is just a K move. So we would like to utilize these instructions. But looking at this code, this implies that an I1 vector is bit-packed in memory. This may be a problem. First of all, for other architectures in AVX2, the I1 vector is promoted to a different type, and it will be a bit hard to bit-pack it. It will be a long sequence of instructions, so we might not want to do that. And when looking at this problem, we've noticed that there has been a long discussion in the community about this. There's a Bugzilla from 2007, which has a lot of info there, and there has been a lot of debates and commits and reverts. So this is, and there are still quite a few bugs open, and probably if you try storing an I1 vector, especially on AVX2, it will break. And what are the options actually? So first option is, of course, byte packing. So each vector element will be in its own byte. And bit packing. So each element will be in a bit. This is, of course, consumes less memory. But as we saw in the previous slide, it is probably not the best option for all architectures. So what are the possible options? at least from the x86 backend point of view? Well, we can do byte packing on all subtargets in x86. And as we saw, it's not the best option for AVX512 because we have new instructions and we naturally want to use them. Also, this is a bit not clear how it will align with bitcast semantics because when bitcasting from an I1 vector to the equivalent integer type, you need to be able to store the vector into memory and load from the same address into the integer. So it's unclear how that can work. Another option is to bitpack on all subtargets, and that can be a problem for AVX512. It will work, of course. And another option that we thought about is doing what's best per architecture, per feature. So bitpacking on AVX512 and bytepacking on AVX2. But this then will lose consistency within even the same target. And that can prove to be an issue. If we have, for example, a library compiled with AVX2 and application compiled with AVX512, it's not clear how they will work together, right? Now, these are the options that we thought about. This is still an open issue, you can say, and we would really want to see this resolved in the future. And another thing to mention is maybe this is not such a common problem because currently from just standard C code, we can't really get I1 vectors in the IR. You need some extensions to make it happen, but probably there are people in the crowd that do manage to somehow use I1 vectors differently. So these were the two challenges that we faced in I1 when generating mass registers in AVX512, and that's all I have, so thank you for listening.
All right, we have time for a few questions. You pick. So to maybe help you solve the common problem, what we do in ARM, we have similar problems not with big packing, but with big mismatch.
Can you just speak up because
Different in different targets. So what we normally tend to do is you pick the one that works the least worse for the other one. So if like big packing is less bad on AVX2 than byte packing is on AVX512, then you pick that one and do by default like you add the feature like a flag or something for the people that say, no, I'm only going to run on AVX512. Because if you compile for one, you can run another x86 with different AVXs. Right? So you don't want everybody to suffer in the worst way possible. So you choose like the least bad one, you make that the default, and you allow them to change.
Okay. Well, that's of course a good idea. Thank you. So we haven't really thought about it yet. And also we need to think about how it works between architectures because if you choose the byte packing option, there's quite a bit of work to do in the target independent code also to make it work. But it is a good idea.
So I have two questions. One, if I1 is illegal, then how things like build vector are going to work without the baseline building? And the second, are you planning to do something same about vectors of other things that are not, that don't divide 3D by 8? Like you have a vector with I3, are you planning to fix that 3 by 8? Are you planning to do anything about it?
So about the build vector and stuff like that, you can still use a wider integer type with these diagonals. You just have to make sure that you properly code-gen the extensions and the truncation. And about the vector of 3 or anything that does not divide by 8, it is also still an open issue. We don't really have a good option, but it is similar, so we assume when we fix the I1s, we will fix this. Here.
As I understand, the problem arises only for when we have one element. It doesn't happen when we have vectors of this. When we work with vectors, when our predicate registers consist of several bits.
Yeah, it's the first problem.
Is it the same problem with vector registers?
No, in vector registers it's okay. We only have the conflict for when you have one I1.
And then like this question. So could we just express this, not use this I1 to express predicate register, but use a vector, one element vector consisting of I1 element?
That is what we had to do when making I1 legal, because you would still need the scalar instructions to somehow emit into a mask register. So we did use a vector of one element of I1 to do so. But
why the problem is still there, then? I mean, if you could in midland separate these two cases, for one predicates use scalar I1, and for other predicates use
I think in the mid-end it would be difficult to teach the vectorizer, for example, to emit scalar masks as vectors. But maybe it is a possibility, but we thought it to be too much of an effort. There's one at the back also.
Which one first?
The closest one. Hi.
This appears to be one of the problems that global ISO is intended to comprehensively eradicate. So I'm wondering if you know what sort of timescale x86 is looking at moving to globalized time.
Well, timescales are difficult. So we are actively working on global ISO. That's all I can say.
So you have the 512 wide vectors now. Are you planning to go wider and maybe do something more generic? Like
Can you speak closer, please?
Are you planning to go wider than 512 and do something more generic like RMSB in the future?
Intel's not that cool.
Yes, no, maybe. I don't know. Any more? Okay.
All right. If there are no more questions, we will have a break until 45, I guess.
Thank you.